Welcome student. My name is Gaurav Sharma from Department of Electrical Engineering. Today our topic is economic of power systems. The art of determining the per unit cost of production of electrical energy is known as the economics of power generation. The economic of power generation has assumed a great importance in this fact developing principle of power system. A consumer will use electric power only if it is supplied at the reasonable rate. Therefore, power engineers have to find convenient method to produce electrical power as cheap as possible so that the consumer are use electricity as a convenient price. The following terms much used in the economics of power generation like interest. The cost of money is known as interest. Deposition, the decrease in the value of the power plant equipment and the building due to the constant use is known as depreciation. The total cost of energy generated can be divided into three parts. Generally, these are the fixed cost, semi-fixed cost, and the running or operating cost. The fixed cost is dependent of maximum demand and unit generated. The fixed cost is due to the annual cost of central organization, interest on capital cost of land, and salaries of high officials. The annual expenditure on the central organization and salaries of high officials are fixed since it is to be met whether the plant has high or low maximum demand or it is generated less or more units. The capital investment on the land is fixed and hence the amount of interest is also fixed. So these all are come into the fixed cost. When we looking to the semi-fixed cost, it is the cost which depends upon maximum demand but is independent of unit generated. The semi-fixed cost is directly proportional to the maximum demand on the power station and is on account of annual interest and depreciation of capital investment of building and equipment, taxes, salaries of management, clerical staff, etc. The maximum demand on the power station determines its size and cost of installation. The greater the maximum demand on power station, the greater in the size and the cost of the installation. Further, the taxes and clerical staff depends upon the size of the power plant and hence depend upon the maximum demand. So these all are come in the semi-fixed cost. So we have to pay the salaries on the clerical staff, we have to pay the clerical staff, to the equipment, to the building. So these all are come into the semi-fixed cost. And finally, this running cost. It is a cost which depends upon the number of unit generated. How much unit we are generated, it is come into the running cost. The running cost is on account of annual cost of fuel, lubricating oil, maintenance, repair, and salaries of operating staff. These all are come under the running cost. We have to consume the fuel, for the maintenance, for pay to the operating staff. So these are coming to the running cost. These charges depends upon the energy output. The running cost is directly proportional to the number of units generated by the station. In other words, if the power station generated more unit, it will have a higher running cost and vice versa. The expression of the cost of electric energy we can categorize into two parts. It is categorized into two parts like three part and a two part. In a three part, in this method, overall annual cost of energy is generated is divided into three parts, where fixed cost, semi-fixed cost and the running cost. That is, total annual cost of energy is equal to fixed cost plus semi-fixed cost plus running cost. The sum of the three costs is equal to a total cost of energy. So it is, which is equal to constant. Fixed cost is the constant. Semi-fixed cost is proportional to the maximum demand. It is the semi-fixed cost is proportional to the maximum demand, and the running cost proportional to the kilowatt generated. Now we can formalize it is equal to the RS which you are paying rupees, and is A plus B kilowatt and C kilowatt hour, where A is equal to annual fixed cost dependent of maximum demand and energy output. B is equal to constant, which when multiplied by maximum kilowatt demand on the station gives the annual semi-fixed cost, and where C is equal to a constant which when multiplied by kilowatt hour output per annum gives the annual running cost. So it is the three-part form. A two-part form is that it is sometimes convenient to give the annual cost of energy in two part. In this case, the annual cost of energy is divided into two part, fixed sum plus kilowatt of maximum demand plus a running charge per unit of energy. So expression for this is A kilowatt plus B kilowatt hour, where A is equal to constant which when multiplied by maximum kilowatt demand on the station gives the annual cost of the first part, and B is equal to constant which when multiplied by the annual kilowatt generated gives the annual running cost. So for the method, various method for the determining the deposition cost, and the deposition cost is the reduction of the value of the equipment and other property of the plant every year due to deposition. So it is called the deposition, and for determining the deposition we have three methods, that is straight line method, diminishing value method and the shrinking fund method. Now the effect of the load variables are: the variable load on the power station introduce many. The effect of load variables on the power station that it introduce many complexity in the operation. Some of the importance factor of the variable load on the power stations are need of additional equipment. The variable load on a power station necessitates to have additional equipments. By way of illustration, consider a steam power station. Air, coal and water are the raw material for this plant. In order to produce variable power, the power of these material will be required to be varied correspondingly. For instance, if the power demand of the plant increases, it must be followed by increase the flow of coal, air and the water. Increase in the production cost. The variable load on the plant increases the cost of the production of electrical energy. An alternator operates at maximum efficiency near its rated capacity. If a single alternator is used, it is have poor efficiency during light load periods. So therefore, in actual practice, a number of alternator of different capacities are installed so that most of the alternator can be operated at nearly full load capacity. However, the use of a number of generating unit increases in the initial cost per kilowatt of the plant capacity as well as the floor area requirement. So the initial cost will increase and the overall area which we are using is also increased when we increase the number of alternator to generate electricity. The load curve it is showing in the figure. The load curve showing the variation of load on the power station with respect to time is known as load curve. How our load is varying with respect to time is shown by the load curve. If you look into the graph, it is clearly mentioned that here is the load in the megawatt and it is the time respect. So how the load is varied as per the time. So in the near about more than 1 megawatt load is there in the midnight, and so it is gradually increased, and near about 6 a.m. and up to 8 a.m. it will go high, and after that it will fall. So as per the time how our load varies with respect to time, it is shown by the load curve in the 24-hour time slot. So it may be seen that the load curve indicates the glance of the general character of the load that is being imposed on the plant. Such a clear representation cannot be obtained from tabulated figure. So we have also the monthly load curve can be obtained from a daily load curve of that month. So we can also create a monthly load curve, yearly load curve from the daily load curve what we are using. So what are the importance of the load curve? We have a few important, like the daily load curve have attained a great importance in generation as they supply the following information readily. The daily load curve shows the variation of load on the power station during different hour of the day. The area under the daily load curve gives the number of unit generated in the day. Unit generated per day is equal to area in kilowatt under daily load curve. The highest point on the daily load curve represents the maximum demand of the station of the day. So at the particular time the load curve shows the peak, like 9 p.m. in the night. So it is the maximum demand, and it also shows the maximum demand of the station. The area under the daily load curve divided by the total number of hours gives the average load on the station in the day. The ratio of the area under the load curve, the total area of rectangle in which is contained, gives the load factor. The important term of the load factors and the factors are the connected load. It is the sum of continuous rating of all equipment connected to the supply system. A power station supplied to thousands of consumers. Each consumer has certain equipment installed in his premises. The sum of the continuous rating of all the equipments in the consumer premises is the connected load. The total load connected is called the connected load. For instance, if the consumer has connection of 500 watt lamp and a power point of 500 watt, then the connected load of the consumer is 5 into 100 plus 500 is equal to 1000 watt. Now the maximum demand, it is the greatest demand of the load on the power station during a given period. The load on the power station varies from time to time. The maximum of all the demand that have occurred during a given period, it is the maximum demand. Thus, referring back to the load curve figure, the maximum demand on the power station during the day is 6 megawatt, and it is occur at 6 p.m. in the evening. So maximum demand we have, what we see in the load curve, it is in the 6 p.m. So maximum demand is generally less than the connected load, because all consumers do not switch on their connected load to the system at a time. So the maximum demand always be lower than the connected load, because what we have a connected load, we do not switch at a time all the loads. Demand factor is the ratio of maximum demand to the power station to its connected load. That is, demand factor is equal to the ratio of demand factor divided by connected load. The average load, average of a load occurring on the power station in a given period is known as average load or the average demand. We are again categorized daily average load is equal to number of unit kilowatt generated in a day divided by 24 hours. So we get the daily average load. Monthly average load, the number of unit generated in a month divided by number of hour in a month. So then we calculate the monthly average load. Finally, the yearly average load, similarly the number of unit kilowatt in a year divided by number of hours in a year. So it is clearly 8760 hours in a year. So then the load factor, the ratio of average load to the maximum demand during a given period is known as load factor. The load factor is the ratio of average demand to the average load to the maximum demand. Diversity factor is the ratio of sum of individual maximum demand to the maximum demand of power station. So diversity factor is sum of individual maximum demand divided by maximum demand on power station. Next is our plant capacity factor. Plant capacity factor is equal to actual energy produced divided by maximum energy that could have been produced. Or we can also get the average demand divided by plant capacity. It is plant capacity factor. Now last is also we can also calculate the annual plant capacity factor, which is annual kilowatt output divided by plant capacity factor into 8760. 8760 is the total hours in a year. Next is plant use factor is equal to station output in kilowatt divided by plant capacity into hours of use, how much hour we are using that particular plant. Next is unit generated per annum. It is often required to find kilowatt generated per annum for maximum demand and load factor. The procedure is as follows, that load factor is equal to average load divided by maximum demand, and the average load is equal to maximum demand into load factor. Now if we have take some numerical, like a residential consumer has 10 lamp of 40 watt each connected at his premises. His demand is as follows: from 12 midnight to 5 am in the morning, he consuming that 40 watt. From 5 am to 6 pm, no load is there. From 6 pm to 7 pm, 320 watt he is consuming. From 7 pm to 9 pm, 360 watt is consuming. And from 9 pm to 12 midnight, he is consuming 160 watt. Now what we have to do, we have to create a plot the load curve and find the average load, maximum load, load factor, and the electrical energy consumption during the day. For this, now we are draw the load curve from the given data, like he is consuming 40 watt from 12 to 5 am and 6 am. So we draw the load curve. Now electrical energy consumption during a day is equal to area of load curve. So now it is equal to 4 into 5 and the 320 into 1 plus. So from this we are calculating the total watt hour or the kilowatt hour. Now average load, the energy consumed during 24 hours. So what energy is consuming is 1720 watt hour energy he is consuming in the 24 hours divided by 24. So 71.67 watt is the average load, and the maximum load is 360 watt, and the load factor is the ratio of average load divided by maximum demand. So we calculate the load factor and the percentage load factor. So the load curve or chronological curve is the graphical representation of load in a proper time sequence and the time in hours. I already told about the load curve, it is the same. The information what we got from the load curve, the load duration curve determines the load variation during different hours of the day. It indicates the peak load, which determines the maximum demand on the power station. The area under the load curve gives the total energy generated in the period under consideration. The area under the curve divided by total number of hours given the load, and the ratio of area under the load curve of the total area of the rectangle in which it is contained given the load factor. Now the utility of load factor is that load curve decides the installed capacity of the power station. It is helpful in choosing the most economical size of various generating units. The load curve estimates the generating cost. It decides the operating schedule of the power station. It is that is the sequence in which the different generating unit should run. When the load element of the load curve are arranged in the order of descending magnitudes, the curve thus obtained is called a load duration curve. The load duration curve is obtained from the same data of the load curve, but the ordinates are arranged in the order of descending magnitudes. Now here in a figure you see the load duration curve. It is clear the daily load curve, those load element in order of descending magnitudes are 20 megawatt for 8 hours and 15 megawatt for 4 hours and 5 megawatt for 12 hours. So it is the load curve and it is the load duration curve. So it is in the descending order. Here we consuming 20 megawatt, here we consume 15 megawatt, and here we consume 5 megawatt for the period of 12 hours, 4 hours and 8 hours. So it is the load duration curve. The following points may be noted about the load duration curve. That is, the load duration curve gives the data in more presentable form. In other words, it is readily shows the number of hours during which the given load is prevailed. The area under the load duration curve is equal to that of corresponding load curve. The area under load duration curve will give the unit generated on that day. The load duration curve can be extended to include any period of time. Now we have different types of load. First is the domestic load. The domestic load consists of light, fan, refrigerator, heater, television, small motor, pump, small household domestic pump, etc. The most of the residential load occur only for some hour during the day. Like we have one graphical representation of the domestic load curve. Like in the 12 at the night we are consuming less load. After 12 we are consuming less load. And after the 6 or at the 6 a.m. in the morning we are consuming more, because at the night time we are sleeping, and at the 6 a.m. generally we are waking up and we are start consuming the energy, and our load curve will increase, and it will be gradually increase and constant up to 6 p.m. and after the 6 p.m. our lightning load and extra load will be turned on, so it will be gradually goes high, and at around 9 o'clock at the night it will be at peak, and after that it will be start decreasing, and this process continuously go on. So it is generally same for the all the domestic load. The dotted line shows the our summer graph and the continuous line for the winters. Next is the commercial load. The commercial load consists of lighting for shops, fan and electricity appliances used in restaurant, etc. This class of load occur for more hours during the day as compared to the domestic load. The commercial load has several variations due to the extensive use of air conditioner and space heater. So for this, from 12 midnight up to 10 a.m. in the morning, it will be a constant. So after that it will increase and go, and it will be fall at around 2 o'clock or 3 o'clock in the afternoon, and after that it will be gradually rise up, and at 8 o'clock in the evening and it will be goes high, and at near about 11 o'clock, 10 o'clock it will be goes down, and it will be constant up to 10 a.m. in the morning. So it will be just like that. And next is the industrial load. The industrial load consists of demand by the industries. The magnitude of industrial load depend upon the type of industry. Thus, small industry required load up to 20 kilowatt, medium industry between 25 to 100 kilowatt, and large industry beyond 500 kilowatt. So industries are continuously working, but during the daytime near about 6 a.m. The load will be goes high, and the lunch period will be 12 a.m. 12 in the noon up to 1 p.m. So it will be a little bitly the load curve will be down, and after that it will be again increase, and up to at last finally at 12 o'clock in the night it will be again decreasing. So in the daytime the curve will be higher. Next is the municipal load. Municipal load consists of street lighting required for the water supply and drainage purpose. A street light consists load is practically constant throughout the hour of night. So if we look into the graph at near about 7 o'clock in the evening, the street light and the pumping house load will be turned on, and up to the 6 a.m. in the morning it will be constant, and during the daytime period it will be 0. Next is the irrigation load. We are providing the electricity to the irrigation field in the night. So near about 10 o'clock in the night, the load will be turned on, and it will be continuously turned on, and up to the 8 a.m. In the morning it will be constant like this. And after that, in the daytime period, no electricity provided to that agriculture area, so it will be the load will be 0. Next is the traction load. The most of the trains are running in the daytime period, so the traction load is generally maximum demand will be occur in the daytime, and the maximum demand definitely occur at the from 10 a.m. to 6 a.m. to approximately 11 a.m. is approximately high, and in the evening near about 5 a.m. to 7 a.m. is the high. The reason from these two time period is that the people are going to the offices, on they are returning to their homes, so reason of the higher at this peak is that. Thank you. That's all for today. Next topic we are discussing in next class.